Metarresters is your partner in lighting performance and surge arrestor technology. This video deepens your technical knowledge of surge arresters, focusing on their core component, Metal Oxide Varistors, MOVs. We will showcase the manufacturing process of MOVs, highlighting the precision and expertise behind high-quality surge arresters used in power systems.
Hello everyone, my name is Florent Giraudet and I work today as a professional consultant in the field of lighting performance and surge arrestor technology. Today we have the opportunity to visit Xi'an Tiangong Electric company, or TGE, which is a major metal oxide varistor manufacturer located in Xi'an, China. MOVs, or metal oxide varistors, are critical components in surge protection for power systems. In today's video, our intention is to educate industry professionals for MOV technologies and surge protection. And we will showcase the state-of-the-art manufacturing process of metal oxide varistors at TGE plants. So we are very thankful that they can open their door to us so we can see their secret and see how they stand out from the crowd.
Before we dive in, let's first understand what MOVs are and their role in surge arresters. Often overlooked, they are crucial components in the power grid. Every surge arrestor design and associated MOVs undergo rigorous testing to showcase its electrical features and prove its long-term stability. Whether we talk about zinc oxide ZNO blocks, metal oxide varistors MOVs, or metal oxide MO resistors, we are discussing the backbone of the surge arresters manufactured today for the electrical industry. In this context, we are referring to medium and high voltage power systems operating above 1 kV AC or 1.5 kV DC, although application exists on low voltages. Surge arresters are used to ensure, as much as possible, an uninterrupted supply of electricity to users, even in the presence of overvoltages caused by lightning and switching surges. MOVs have unique nonlinear characteristics that help limit overvoltages and divert excess energy safely to the ground. Did you know that the core of every modern surge arrestor is simply a stack of MOVs? These MOVs are strategically stacked to form a column, each designed with a specific approach to ensure compression and maintain the integrity of the MOV column. But how does the MOV structure play a role in power systems? To achieve the desired energy handling capacity, charge transfer capability, or a specific residual voltage under impressed currents, it's essential to have the right number of parallel paths within the MOV to support current flow. This is controlled by selecting the appropriate diameter of the MOV. Typically, the diameter is limited to around 120 mm due to construction constraints. For higher performance requirements, multiple MOV columns are connected in parallel within one or more surge arrestor housings. In summary, the diameter of the MOV directly influences its ability to handle high current densities from transient surges without sustaining damages. Each boundary layer between two ZNO grains has a breakdown voltage of approximately 3 volts, depending on the structure. To achieve the desired overall breakdown voltage for a specific application, the MOV must contain the appropriate number of serial grain boundaries. However, due to production and testing constraints, the height of MOVs is generally limited to around 45 mm across all manufacturers. Therefore, in high voltage surge arresters, multiple MOVs are stacked to meet the required performance. In summary, the height of the MOV is critical for managing temporary overvoltages and ensuring stable continuous operating voltage throughout its service life. Let's briefly explore the history behind this technology to fully grasp its significance. This MOV technology became prevalent in the 1980s and is now completely dominant. Through the historical development, distinct eras reflect evolving challenges and innovation. Pre-1930s solution relied on rudimentary spark gap arrestors. Post-World War II, silicon carbide arrestors gained favor but proved insufficient for addressing complex issues like switching surges and AC follow current. The rise of advanced power systems in the 1970s led to the adoption of MO surge arrestors. The Japanese industry pioneered this technology, overcoming initial limitations related to lifespan and power loss. Today, MO arrestors are industry standard, highlighting the continuous evolution in this specialized field.
Thanks a lot for opening the doors of your new factory. It's really a pleasure, and it's truly impressive to see the size of the buildings and the potential production capacity that you have right now. Can you please give us more details about this new manufacturing plant?
Xi'an Tiangong Electric has been dedicated to the research and development of zinc oxide varistors for nearly 40 years. Founded in 2002, the company has consistently focused on developing new products and enhancing product quality. The facility you see here is our new factory, spanning approximately 70,000 square meters, with a full production capacity of 350 tons per month. We boast a large team of engineers who work tirelessly to ensure our products meet a wide range of customer needs. Internationally, our product quality is regarded as being at the forefront, and the stability of our product performance is superior to that of other manufacturers.
And I know that TGE has been a major player in the MOV industry for many years. Can you maybe share some historical facts and describe the unique expertise of TGE?
Tiangong Electric has a large R&D team with many professional engineers focused on enhancing the performance of zinc oxide varistors. Given the long production cycles and the irreversible nature of many manufacturing processes, we place particular emphasis on two critical steps: firing and granulation. We deploy a significant number of technical staff to monitor and track our products, ensuring stability in performance through meticulous process control during production. If a deviation in performance occurs, we promptly investigate it, and if the change proves beneficial, we swiftly implement the improvement into practice.
We will now walk you through the step-by-step process of creating MOVs. There are generally 7 key steps involved in producing the final product. Weighing and mixing. The process begins with weighing and mixing the raw materials. Dehumidification or spray drying. Next, the dehumidification process prepares the material by removing moisture. This next step is crucial for preparing the mixture for the next stage, pressing or forming. The material is then pressed into an initial shape, giving the MOV its preliminary structure. Pyrolyzing and sintering. Once the MOV has its initial shape, it undergoes pyrolyzing and sintering. These processes remove certain compounds and help form the grains and grain boundaries, resulting in the MOV losing approximately 50% of its initial volume. Passivation or coating. After sintering, a passivation layer is applied to the lateral surface of the MOV to provide a protection against environmental factors. Surface preparation and electrode application. The next steps include surface preparation and the application of electrodes. These steps are essential for facilitating the stacking process and ensuring proper conductivity between the MOV blocks. final verification and testing. Finally, electrical tests are conducted to verify that the MOV meets the specified characteristic for electrical performance and energy capacity.
So we are here at the beginning of the manufacturing process of the Metal Oxide Varistors. This is one of the first steps, the weighting and the mixing of the different constituents. MOV blocks are primarily made of zinc oxide material, about 90%. The residual additives represent about 10%. In this process, we're gonna mix the zinc oxide material that you can see here together with the additives which are prepared up front, depending on the recipes, depending on the requirements, to achieve different functions. The zinc oxides and the residual additives will be mixed together with organic solvents and binders to obtain a slurry. This slurry will be then injected in those spray dryers. So the spray drying process is important to remove the liquid contents and obtain the final powder, this powder that will be used for the next step. Can you tell us a little bit more maybe about the capacity of this process and maybe about the quality control?
As you can see, this is our spray granulation process. The production of oxidized granulation powder directly affects the electrical properties of the MOVs. Key factors such as the control of the granulation powder's particle size, the internal temperature of the granulation tower, and the uniformity of various component concentrations all significantly impact the Varistor's performance. Currently, we operate 4 granulation towers with a combined capacity of about 350 tons per month, fully meeting the delivery needs of many customers.
The next step is a visually significant part of the process, as dehumidified powder is pressed into the preliminary shape of the block. This dry pressing process is where the MOV begins to take form. At this stage, each block's weight is meticulously measured to ensure precision and quality. Did you know that the IC classification of surge arresters is closely linked to the diameter of the Metal Oxide Varistors? When you dive deeper, it gets a bit more nuanced. The QRS rating, repetitive charge transfer, is directly connected to the performance of the MOV itself, while the WTH rating, thermal energy, involves not just the MOV performance, but also the thermal dissipation behavior of the surge arrestor design.
So it's really hot here. We are near the ovens where we have the pyrolyzing process and the sintering process. After the pressing, we obtain this block. This is the first shape of the block. The first part is the pyrolyzing process, where we are going to remove the organic solvents and binders from the block. And we are going to obtain this green block. So this green color is actually the normal color of Metal Oxide Varistors. So first step, pyrolyzing process to these ovens, these tunnels. Once we have obtained the green blocks, we're gonna go through the sintering process where we're gonna reach much higher temperatures, up to 1050 degrees. Then the block will become black. Actually, it's just the outsides. The inner part is still green. But after the sintering process, we obtain this block and this will form the grain boundaries to obtain the desired requirements, the electrical performance. Can you tell us a bit more about this process? Because it has been built from scratch, though these are Unix ovens.
As you can see, these are our 11 tunnel furnaces with a capacity of about 400 tons per month. These furnaces are custom-designed, non-standard equipment developed by our company to meet specific temperature control needs, such as ensuring uniform and stable furnace temperatures. Additionally, the furnaces support rapid cooling curves, which are crucial for achieving the desired electrical performance of different metal oxide varistors. The temperature profile of the tunnel furnace is fundamental in determining the electrical properties of the varistors.
And I heard that during the development of this process, you also have improved the heating system. Can you tell us more about this, the way you reuse the heat from the oven?
As you can see, the pipes above the tunnel furnace are a way for us to obtain waste heat because the temperature in the furnace is particularly high and the energy in this part is very huge. We transfer the temperature of this part through the way of bubbles and then use it for the supply of hot water in the company. Including other processes, need hot water from our stove here to take the temperature, played a role in energy saving and environmental protection.
The next step involves applying a specialized passivation layer to the lateral surface of the MOV. This layer plays a critical role in protecting the MOV from environmental factors, while also enhancing its flashover resistance. It's a highly sensitive process and one of the key expertise required for producing high-quality MOVs. Due to the proprietary nature of their manufacturing techniques, TGE cannot reveal every detail of this process. However, what we can show you is one glass coating process at TGE. Glass coating represents the cutting edge of MOV technology. This process consists of two critical stages. First, the application of dry glass powder, followed by a sintering process to finalize the coating.
Right after the glass coating process, we obtain a block like this. So you can see that there is still a glass coating on the top of the block where we want to apply the electrode. So we are going to prepare the surface by grinding on both sides so that we can apply the electrodes, the aluminum spraying afterwards. So this machine here is grinding several blocks together. So right after the surface preparation, as we have seen before, with the grinding process, we have obtained a very clean surface, a very proper surface, but we can now apply aluminium. So this is the aluminium spraying process, where we are going to obtain this surface, the aluminium electrodes. This is very important to have a proper surface, because inside the Metarresters, the MOV will be stuck on each other. This is very important to ensure proper conductivity, but also to make sure that the energy or the current impulse is properly or evenly shared to the block. Okay, so this is the last step of the manufacturing process of a MOV block, the testing. So typical tests, which are done on surge arresters, or original voltage tests and reference voltage, which are done as a routine test, 100%. So also for the MOV block manufacturers, they need to go through this testing, this electrical test. But there is one more test which is very important. This is the long duration impulse test. So we have, in that specific case, we have an MOV of 48 millimeter diameter. We are going to inject on every block a rectangular wave shape of 800 amps for 2 milliseconds. So this is a lot of energy. This is why you see those sparks in the testing equipment. This is very important to perform this test on every block to make sure that we have achieved the proper characteristic for the block, the properties of the grains, the boundaries, etc. Hi, Mr. Ling. Nice to meet you.
Nice to meet you.
So you're the quality manager at TGE.
Yeah.
And here we are in a special area where we do in-process testing. So sample tests to make sure that the blocks that are produced can withstand a certain energy level, long duration impulses. Can you tell us a little bit more about this in-process testing and maybe what makes this equipment a little bit special?
This device is a new multifunction impulse current generator that TGE will soon put into operation. It can perform high current tests of 200 kiloamperes for Metal Oxide Varistors below 10 kilovolts DC with a 4/10 microsecond waveform, 100 kiloamperes for 8/20 microseconds impulse current, 40 kiloamperes for 1/10 microseconds steep wave impulse current, 65 kiloamperes for 2/20 microseconds impulse current. This meets the testing requirements of both IEC and IEEE standards, as well as arrestor operating duty tests and TOV tests. In addition, TGE has newly upgraded a set of rectangular wave impulse current testing equipment. It can perform 2 millisecond rectangular wave impulse current tests of 3,000 amperes on a single DC 8 kilovolt metal oxide varistor, meeting the testing needs of UHV project lightning arrestors in our country. It can also carry out 200 to 230 microseconds QRs 4C impulse current tests on 500 kilovolt line arrestors. TGE's high voltage testing equipment can meet the testing needs for metal oxide varistors from 3 kilovolts to UHV 1000 kilovolts lightning arrestors.
From my experience, I think it's very important, very critical to have this capacity. So we are here in the aging laboratories. This is an additional testing, an additional critical test, which is performed as a sample test, so in-process inspection on every production batch. So it's important to keep in mind that during the development of metal oxide surge arresters in the 70s, it has been a challenge to maintain the performance over time because the surge arresters is continuously under voltage. So the idea is to guarantee the performance over the service life, would be 40 years or more. So in this process called the accelerated aging test, we are gonna apply some critical condition to simulate aging. So we have ovens which are heated at 115 degrees Celsius, and we apply a continuous voltage across the MOV block for 1,000 hours. So the voltage is actually 20% higher than the continuous operating voltage of the block. And with this process over 1,000 hours, we can demonstrate that the power losses of the blocks are decreasing. Therefore, we can guarantee the long-term performance of the block and that the characteristic, the electrical performance, will not decrease over time. Can you give us more information about your setup here as a very important part of the quality control?
Okay, our aging test equipment is quite comprehensive. One of our aging test chambers has 4 stations, allowing us to test 4 batches of metal oxide resistors simultaneously. We conduct random aging tests on each batch of products before they leave the factory to ensure product stability. We typically perform accelerated aging tests at 115 degrees Celsius with a 90% charge rate, equivalent to 1,000 hours at 1.1 UC. Additionally, we can perform a 1,000 hour DC polarity reversal aging test. Last year, we conducted a 2,000 hour aging test study on resistors used in shielded separable arrestors. And this here is the 2,000 hour aging test curve. Our aging curves are generally monotonically decreasing with aging coefficients less than 1, ensuring the long-term stability of our resistors.
Metal oxide varistors may seem simple, but the precision and expertise required to ensure consistent production quality are critical. We have only scratched the surface of the process related to MOVs. The journey of manufacturing, testing, and installing surge arresters in the field is extensive, involving numerous steps to ensure reliable equipment that not only meets international standards, but also achieves the highest levels of industrial excellence. We extend our gratitude to TGE for the opportunity to showcase their manufacturing facilities and illustrate technical concepts through real-world production processes. Thank you for watching. Stay connected by following us on LinkedIn, where we share new content every week on surge arrestor technology and lighting performance. And don't forget to subscribe to our YouTube channel for exclusive video and insights. For more information about Metarresters and how we support the electrical supply industry in managing lighting disturbances and surge protections, visit our website.